Yeah. I don't know if this is left here.
I mean, I never really. I should just like open up an eBay. You know. I think a little bit. Maybe homework 11 and activity 7. I think. Does that sound about right? Yeah, if I always move it, it's always a conservative move. It always gives you more time. It won't give you less. Okay.
How do you know when to use pooled variance versus?
Yes.
Excellent question. Excellent question. Okay, so about the final exam. Oh, you guys are interested? Okay. So what's going on? Let me just kind of cut to the chase. Okay, so this is an announcement that you want to read. There's two in particular. Kind of the bottom line is this. Just step you through this really quickly. If you go to modules and go to the bottom on exams, okay, there's a new little tab there. And there are 2 documents. So the first is the list of exam 3 topics. So these are all the things that you're responsible for exam 3. This is a practice exam. So what you want to do is go ahead and print both of those out. I would look through the list. And as I'm looking through the list, I would go through my past homeworks and my past quizzes, see which ones you missed, which ones you need to reinforce, which of these topics, okay? After you get done with this, go ahead and work exam 3. Exam 3. So on Tuesday in class, we'll go through practice exam 3 along with any other questions that you have for exam 3. On Thursday, we'll have an in-class practice final. So if you bring your laptops, you take it in class. If you do, I'll give you some extra points on the final exam, which is the most heavily weighted component of this class. So just don't miss out on those extra credit points. On Saturday, we'll have a review session for the final. When is the final? The syllabus will tell you, right? So look in the syllabus and find out, all right? That's pretty much all for those announcements. Now, someone asked the question, some people had problems with one of the homework questions, and it had to do with pooled variance. So when you're working a 2-sample unpaired t-test, every once in a while it will say assume the variances are equal. And when it says that, you'll notice there's a little box in that StatCrunch, right, that will say pooled variances. Go ahead and click on that and use that. I'm not going to give you anything on the exam that's going to require you to do that, but it'll help you get to the homework. So I gave you some extra attempts, and I extended the due date if you need to redo them.
So you say there's a list of topics, so can we assume the exam is a watered down final?
No, the final is totally different than exam 3. The final covers everything. Yeah, exam 3 only covers inference, okay? But the final covers everything. That would be a really bad assumption. Oh, one other thing that you shouldn't assume, speaking of assumptions, is please don't assume that the practice exams are going to be like the actual exam. So they're a preparation. They help get the concepts down solid. But please don't think, oh, the practice exam, there was one question on 2-sample unpaired, 2-sample paired, so the exam is going to be like that. All right. I mean, in real life, you want to be able to work new problems, okay? So they aren't going to be cookie cutter. Okay, though. Any other questions? Any other concerns, comments? Yes, sir.
Out of all 4 exams, how hard did you say
the so speaking of working the whole semester to understand the concept, I think they'll find that the final is easier than any one of the single exams. But if you're trying to do it the last minute, trying to catch up and cram, it's just the opposite. So it really depends upon you. So what sort of final are you going to have?
I don't know. And there's no way to do 2 attempts on questions, especially like the multiple, like the number ones, because I know when you give 2 attempts for the exam, my first exam is a lot less than my second exam, and that's just because sometimes maybe like there's like a little mistake with numbers, and I know how to do it, but I might have input one little thing wrong. So that really affects like the variety of the 2 grades.
And so I definitely go back and look at those, and if you have those sorts of concerns, please come and see me. On final, I give you guys scratch paper. I encourage you to write down your work, what you do, turn it in, and I actually go through the final person by person, question by question. But if you do, and you know, one of the things that I actually like about Pearson a lot is that it really forces you to go back and look and see what you did wrong. Usually when an instructor, in my case, my own experience, when I was in grad school, I had a class I was totally lost in. Professor wrote these beautiful long comments. It was like me trying to teach calculus to my dog, right? I didn't understand anything when he was writing. But the thing about the Pearson is it makes you go back and look and try to figure out, okay? So if you're totally convinced that you got it right, you probably did get it right. It probably is an error. Then come and see me. If not, still come and see me, and it'll be a good learning experience. So I think this is a real benefit. Okay, we're all good? All right. So what we want to do now is we want to continue on with regression. We're going to finish up. So last time we said, okay, regression helps us look at relationships between two quantitative variables. And so as an example, we looked at how mileage affects the price of a used Porsche. We went ahead, we took a random sample, and we said, okay, what do we always do with data? This is not just for regression, right? Any data set. We plot it, we describe the plot, and then we compute summary statistics, numbers that capture the things that we're describing. So for regression, we always make a scatter plot. The three things we're describing is the type of relation, if it's a linear relation, the direction, and then the strength. And these two pieces of information quantitatively summarize that. So the correlation coefficient, it captures the direction and the strength, right? The regression coefficients give us the details about the linear relation. And now we have to go to the probability model. This is always the hardest part by far, right? So it turns out that the key to the probability model is understanding what a residual is. So every single data point has a residual, and what the residual is it's the y value for the data value minus the fitted value on the line. And so it's kind of like the residue. It's what's left over, okay? Basically, if I wanted to write y, I could write y as y hat plus an error term, and that's the residual. So it turns out that when we're doing regression, just like if you kind of think back, this is a good thing to start to do now, putting things together. When we do any sort of inference, we always have to ask ourselves, what assumptions have to be satisfied, right? So for one variable, when we were looking at the mean, what did we need? We needed the central limit theorem, which meant we either needed a really large sample or a nice variable, right? Same thing here, we have three assumptions. The first is a little bit tricky. It says the data points have to be drawn from a random sample, and you might say, how hard is that? We've been saying all we have to do is just let a computer randomly choose values and we're fine. But there are times when you don't get data sets like that. Classic example is finance. When you're looking at time series, okay, you're looking at, for example, the price of an individual stock. Those values are not independent. As the stock begins to go up, it's more likely to go up. The average, the Dow Jones average, may go like this, but individual stocks don't, okay? So this is a situation, if you were looking at time series and trying to do regression, which is what a lot of people do, we would have to be really careful about this, okay? We're not gonna deal with that. We don't have to worry about that. Our big concern is gonna be the residuals. And the key idea is that the residuals have to be approximately normal. Well, now think back, again, putting things together, right? We know how to figure out if a variable is normal. What do? We plot it. We see if it's kind of symmetric, right? If it is, we do a QQ plot to test for normality. And if we're really unsure, what do? What's our last step? Run a Shapiro-Wilks hypothesis test for normality, okay? We're not going to get that involved, okay? We're basically just going to plot it, look at the plot of the residuals, and then we're going to go ahead and make a QQ plot. We're rarely going to do a hypothesis test. Okay, this last condition is not going to concern us greatly. And so what it's saying basically is that just like if you had a single variable, you could have an outlier, and you have to think about the outlier, right? The same thing is true for regression, except now it's a little more difficult because you can have an outlier in X or an outlier in Y. You have two coordinates. We're not going to deal a lot with this. I'll kind of tell you what I want you to know at this point. Okay, so how do we do this? It's actually really easy. So we're going to go back and we're going to go use the Porsche data. And we're going to run the same command we did last time, stats, simple linear regression. And now what we're going to do is we're going to check a few more boxes. Remember last time, we only filled in the X and Y variable, and that was it. Now we're going to plot some graphs of the residuals. So we're going to choose residual versus x in QQ plot of residuals. And then we're going to go ahead and we're going to save the residuals themselves, and we're going to make a histogram and a box plot of the residuals. So let's go ahead and do that. So go into StatCrunch. Connection's a little slow today, isn't it? So go ahead and when you get that, put in the x and the y variable, and then click on the graph residuals versus x in QQ plot of residuals, and then click Save Residuals. Oh, the Porsche data set that we had, right? The used Porsche data set. This is taking a little while on mine. Let's just see how it moves. Yeah, it's really slow today, isn't it? Yeah, like just long. Wow. Okay, you got it. Yeah. Just go to just go to stats regression, simple linear regression. Sometimes I find if you keep on trying to refresh, you just catch it at the right time.
Was there data where you saw it?
I'm sorry?
Was there any data where you saw it?
Right, that was the Porsche data set, the one we were using last time. We'll just use the same one. Oh, wow. This is ridiculous. Okay. How's everyone else doing? So the two that you want to plot will be right next to each other. QQ plot of residuals and residuals versus stats. Good, good. So you guys are getting it. Try it one more time. Okay. Okay. So well, fortunately, I have it worked out. Okay, so I'm gonna. I have the stuff already done, and you can do it afterwards. Okay. So if we look at this plot, so if you look at your output, and that's okay if you don't have it yet. That's all right. When you get your output, what you'll notice is there'll be one page that looks exactly the same as last time. But if you look at the top, you'll see like 1 of 3, right? So when you click through, this plot will show up. And this is the residuals versus the x coordinates. So this is the mileage for each of the data points. And this is the residual for each data value, okay? So this, for example, was a point where there was 20,000 miles and the residual was about minus 0.2. In other words, this was 2 below the line, all right? Now, what are we looking for? How do we interpret this? Well, we're in our mind's eye drawing a line through 0. And what we want is we want the values to kind of bounce around 0 randomly. So here's what we're kind of looking for. We're looking for two things. First of all, we're looking to see that there's no trend in the residuals. In other words, if I saw a residual plot that looked like this, it's very clear that there's still a trend left over. What does that mean? That means that a linear model is not good enough. I needed a more complicated model, right? After I subtracted off the linear part, there's still a trend left, okay? So we don't want that. The other thing also is we're also looking for independence. And what that means is this. When it isn't independent, here's how it looks. This is 0. What happens is the data values look like this. We don't want that. So this isn't really a trend, but this is clearly not independent. If this one's positive, the next one's negative, okay? So we kind of want this like sort of picture like this. So what does this look like ideally? Ideally, the residuals should look like this. They should kind of be scattered around 0, and you should be able to draw a tube that's symmetric about 0, and it's kind of filled up by the data values. Of course, we never get this in real life. This kind of looks like this, but not quite. One of the things we're looking for is we're looking to make sure also that the standard deviation doesn't change. So this is a case that as x increases, the residuals have a larger variation, okay? So this is what we're trying to weed out also. We want what we call constant standard deviation. That's why that nice uniform tube wants to contain these guys here. So if you look at these words, this is called homoskedasticity. This is called heteroskedasticity. Say that 3 times twice, okay? So there's your $10 word for today. So we're looking to see that we don't have something like this. And so this looks okay. So that residual plot looks okay. We're looking at the QQ plot. We know that we're looking to see if it's linear. This looks pretty good. There's a little bit of variation, but nothing all that bad. There is one outlier. So one of the things you want to get used to when you're looking at data sets, as soon as they get above 20, you very often are going to have one outlier, right? So we have 30 data values. This one value wouldn't cause me to throw the baby out with the bathwater. I'd say this still looks pretty normal. You guys have heard that phrase, right? Yeah. Really? Oh dear. Okay. Well, there's your homework assignment for tonight. Maybe with the bathwater. Okay. Now, notice that we didn't plot the histogram of the residuals, and the reason why is very often the appearance of the histogram is kind of jacked. This is the classic example. So if you actually plotted the histogram, did anyone plot the histogram of the residual? Okay. So it looks really weird. What are we looking for? We're looking to see if the residuals are normal. We want to see this nice curve. Are we seeing this? Okay, so you have to ask yourself, what's going on? Is this data skewed? Now, I don't think it is. And the reason what makes me think it's not is because if it was skewed, it would be left skewed, right? But notice what's going on with the left skewed distribution. The mass is more toward the back end, right? If you look carefully, you don't see that here. You see the mass kind of at the center, and then it cuts off. And what this makes me think is this makes me think that the shape of the plot is an artifact of the bin width. And that's something we haven't dealt with a lot. But with histograms, if you change around the bin width, very often the plot can look very different. So let me illustrate. You guys have saved the residuals now, hopefully. And hopefully mine has loaded. Okay, so if you, I'm going to try to change the bin width. So if you go into StatCrunch and you go ahead and plot the residuals, so if you computed them, you'll see a new column with the residuals for each of the data values. The smallest residual is -19. So I'm going to start the bins at -19 and make a bin width of 6. And if you do, what you'll see is, unfortunately I can't show you, but it's actually a lot more symmetric. Let me see if I can get this to work.
What values did you change those in?
Right. So the smallest. Okay. So you start at -19 and you make a bin width of 6. And unfortunately, I'm not going to be able to show you guys. Do you have it?
Yeah, I do.
Okay. Do you mind if I raise your laptop? Is that fine? Okay. I'll be really careful. Okay. So this is what it looks like when you change the bin width. It looks very different, doesn't it? So this bin width can make a big difference. Now, does that look symmetric to you? So here's the thing. You might think it's not because the two sides look a little different. But when you do this histogram, what you'll see is that these frequencies, so he's plotted frequencies. This frequency, really careful. This frequency is 2 and this frequency is 3. So it turns out that there really isn't that big a difference. So this looks a lot more symmetric, okay? Thank you. So let me ask you a question. Suppose you wanted to think about how to plot the residuals. Are there other ways that we could have plot the residuals? Other ways that we can plot a quantitative variable? What other ways do we have? Is the histogram the only thing we can do? A box plot? A dot plot? What would be the best plot maybe to look at for symmetry here? And why? Well, I would say box plot is better.
Yeah.
Because why? Well, the box plot doesn't get caught up in all the details. It's like a grosser picture. So if you go ahead and make a box plot and put the mean on top of and put the mean and the median on there. Yep. Excellent. Very good. Okay. Can I raise them? Yep. Okay. This is what the box plot looks like. Okay. Notice that the mean and the median are both plotted on here, okay? They're on top of each other. So when you're looking at a box plot and you're trying to determine if the distribution is symmetric, what do you look at on the box plot? So one thing's the mean and the median. They're right on top of each other. What else do you look at? Not so much that, and you know, when you look at this, you can't even see that they're actually both here. So maybe you don't even know the mean's plotted. So what else are you looking for? I'm sorry? I can't hear. Sorry. But what about the IQR though? How's that going to help me? What features of the plot am I looking at? Right. Where is the median? The median's in the center of the box, right? What else am I looking at? The whisker line, because that's evidence of skew, right? So you notice the median is almost flat in the middle, and the whiskers are about the same length, right? So this is very strong evidence that this thing is symmetric. Thank you. You're a lifesaver. Okay, so here's kind of the moral of the story. People throw things in a computer and they compute something and they think like it's handed down from God, right? But you have to think about what you're doing. Notice if you had gone with that first plot, you would have said that I can't use a regression model because you would have assumed that it's not symmetric. But when you think about how to plot it, and you're careful, you realize that it actually is. Now, you might say that I kind of jury-rigged that. So and one of the arguments people make against statistics is, well, you can do whatever you want with data. But here's why this isn't true. This is what you want to think about. Very often in statistics we guess. So I guessed. Hold on. All right. So when I thought. So here I guessed. You know, I guessed that it was not left skewed. And I plotted the histogram, and it seemed like it was kind of symmetric when I messed around with the bin widths a little bit. The other thing is that when you guess properly though, and you do the analysis carefully, everything else is self-consistent. So notice that the box plot was consistent with the histogram, okay? So we're not making things up. When you get the right interpretation of what right way of looking at it, everything kind of falls together. Okay? All right. So, and again, if I had the box plot, you could see, but the median's right on top, the mean's in the center, the whiskers are the same one. Okay, so what do we need to know about this last assumption, outliers in X and Y? I'm not going to ask you to do a lot except just to recognize when they're present, okay? So in this data set, this is an outlier in Y. This is a data value that's very far off the line, okay, vertically. Notice what this person did. They have very good practice. What they did is they actually ran the line with and without this data value. It's always a good thing to do when you have outliers. Run the analysis with and without. So without this point here, they got this line. When they added the point, what did the line do? It moved up, right, towards this point, okay? Outliers in X are a little trickier. This is a data value that's far away from the others. Notice what the effect of an outlier in X is. it tends to rotate the line. This is the line without this data point. With this data point added, the line rotates. We're not going to get into this, but there's actually a way of kind of quantifying that. So there's a term that we use called leverage. And leverage looks at, for each data point, how much the line rotates with and without that data point. So this point would have really high leverage, okay? The only thing I want you to know how to do for the exams is just to recognize you have outliers. You should look at it, and if you were going to describe this, you would say this is a strong, positive, linear relationship with one outlier in Y, and that's it, okay? Okay, so now we're to inference, and this is really the fun part. So this is really an important equation here. There are two facts in this class that are really kind of central. The one is the central limit theorem, when we're working with a single variable. When we're working with more than one variable, this is a really fundamental equation. So this is what we call the regression equation. It says that any random variable, the way we model it, is we think of it as the mean plus a random error term. When you think about it, even with one variable, this is how we modeled, this is how we modeled single variables. So we said that, x was normal, right? Well, think about what this means. This means that we can write x as mu plus an error term. So even for a single variable, right, this is like the origin, mu, right? And then the error term is telling how far off of mu I am. What's different with regression is the fact that now the mean is a function of x. So this is something new. When we worked with a single variable, we said the mean was a fixed unknown number, right? But now we're working with two variables. So now the mean of y is going to be a function of x. And that makes perfect sense, doesn't it? It makes perfect sense if you think about the Porsche example, that the average price for a Porsche should be a function of the mileage, right? The x variable, okay? So this is kind of the picture that goes with this model. The idea here is this is the xy plane. This is the regression line. And the idea is that if I look at a specific value of x, say small x, and now I ask myself, what do the y values look like, okay? So I fix this value of x, and I want to know, what do the y values look like? They have a normal distribution. So notice how the normal distribution comes into play yet again. Okay, for one variable, we need it for inference. We need it for two variables. So if we fix this particular x value and we looked at the y values, they would have this normal distribution. So one of the things that you have to bear in mind that can be a little tricky, and if you guys did, I think what was it, quiz 6, you started to notice this. There were these questions about confidence intervals. And they started mixing up the variable and the sample mean, right? So you always have to think about what am I looking at? Am I looking at the variable in the population, or am I looking at a sample? So when we're looking at the population, this is the regression model. When we're looking at a sample, this is the regression, this is the estimated regression model for the sample. So this term here, beta naught plus beta 1x, this is the mean of y for a specific value of x. And these things are parameters. So we talked about these on Tuesday. Beta naught is the y-intercept. Beta 1 is the slope. Okay? Those are the things that we want, but we can't get. So what do we get? We get this equation right here. This value y is often called y hat, or sometimes the fitted value of y. And these things here, b sub 0, this is an estimate for beta naught. This is our estimate for what the y-intercept is. And b sub 1 is the estimate for beta 1. In other words, it's the estimate for the true slope of that regression line. Epsilon is the random error term. This thing is normal. E is the residual, and it's approximately normal, and that's why we're doing all these tests for normality when we're looking at the residual. So you have to bear in mind these two different things, what they're saying, and the symbols here that we're using. So let me give you another way of looking at this. Suppose, for example, this was a scatter plot for a population. Suppose I had the population. So this is the true line. This is the model right here. And this thing here, beta naught plus beta 1x, this is the true regression line. Now I get data. So notice some of these dots will become blue, right? So I collect a sample, some of these data values, and I get my estimated regression line. They're not the same, right? And we kind of expect that. We know that the estimates from a sample are never the same as the actual values of the parameter we're trying to estimate. So this is what we get from our sample. So here's a really important slide. We want to ask ourselves the most basic thing we want to do is we want to ask, first of all, is there even a relationship? Before we go into all the bells and whistles and try to use the model, if there's no relationship, there's no reason to use the model. And so we want to phrase this in terms of a hypothesis test. So the null hypothesis, null means nothing's happening, right? So the null hypothesis is that there's no relationship. The alternative is that there is a relationship. There's a linear relationship. Now I want to recast these two hypotheses in terms of a test on a parameter. So how do we do that? So here's the idea. So if the null is true, there is no linear relation. And what the scatter plot must look like is something like this. There's no trend, right? It's just like a cloud. So let me ask you a question. If you had to fit a data set like that with a single line, what line would you use? Maybe not totally obvious. What do you think would be the best fit line? I would argue just a straight line. So this straight line would be my regression line. Now, why is that? You might say, I don't believe that. If I do this line, it's going to fit the points equally well. So here's how we think about the regression line. Remember what it's doing. It's predicting the average value of y, right? So we're trying to predict y. If there's no relationship with x, and I have to pick a single number to predict y, what am I going to use? I'm going to use the mean, right? So it turns out that this is a line y equal to y bar. So dx and this is the y coordinate. Okay, so this is the line y equal to y bar. What is the slope of this line? 0. Okay, so if there's no linear relationship, the slope is equal to 0. And what's the symbol that we use for the slope? Pop quiz. Beta 1. Beta 1. Good. So notice this is the null hypothesis. The null hypothesis is that beta 1 is equal to 0. Okay. Now, conversely, if there is a relationship, if the alternative is true, there is a linear relation, which means that the points are following a linear trend, right? So they're looking like this, or they're looking like this. What sort of relationship is that? Positive, right? So what would the slope be here? It would be what? Slope would be, well, it would definitely be greater than 0. We could say that, right? So here beta 1 would be greater than 0. Here the slope would clearly be less than 0. So notice in both of these cases, what can we say? Beta 1 is not equal to 0, right? So the alternative is that beta 1 is not equal to 0. Okay? This is the hypothesis test we're going to run right here. So notice how we kind of morphed everyday language into a geometric understanding of what's going on into an actual statement about a test on a parameter. All right? So here's the picture. No relation, flat line, slope of 0, relationship, slopes not equal to 0. Okay? Any questions on the hypothesis test? Everybody's good? All right, so we actually want to see how this works. So let me see if I can get this to, if this thing is fine. So here's what I'd like you to do. What's that? Yeah, maybe that's the only thing I can do. Here, let me just try this really quick. So here's what I'd like you to do. I'd like you to go back and look at the output that you got for the Porsche, okay? We actually have this output already. And here, I'll show you. It's on another slide. Okay, this part seems to be working okay. Come on. That's okay. So if you go back here, notice that this is our output, okay? And what we're doing is we're looking at the slope and we're looking at this p-value. And so this p-value for a slope is the p-value for this hypothesis test. Now, the way that we draw conclusions from hypothesis tests are the same for any type of hypothesis test. The same as what we did when we looked at mu. So what would our conclusion be here? The p-value is 0.0001. What would we conclude? Reject the null or fail to reject? Reject the null. So what would we say? Well, we would say that at a significance level of at least 5%, right, we conclude that there is enough evidence that there's a linear relationship. Okay. So we're basically saying that we reject the null, we believe the slope's not equal to 0, we believe there's a significant relationship. Okay? All right, good. Now, there's some other types of inference that we can do that are. So one of the things we can do is we can do confidence intervals, okay? So first of all, we can go ahead and we can estimate a value of y from a given value of x, okay? So for example, if I want to know what is the estimated average price of a Porsche with 50,000 miles on it, all I have to do is put those guys into that equation. That should be plus, by the way. Let me change that really quick. Okay. Okay. But we can do some other things. For example, we can compute a confidence interval for the average price. Hold on. So just like we can compute a confidence interval that contains the average value of a variable, we can compute a confidence interval that contains the average value of y. So you might want to know what is a 95% confidence interval for the average price of a Porsche with 10,000 miles on it. We can do that. The last thing we can do is really cool. So suppose you're out looking for a Porsche, and you compute a confidence interval. And let's suppose that confidence interval is maybe $45,000 to $60,000. And so you go to, and so you say, okay, with a Porsche that has 50,000 miles on it, the confidence interval is $45,000 to $60,000. What does that contain? That contains the average value, right? So you go to look at someone's Porsche that has 50,000 miles on it. They want 65,000 instead of that 60,000 that's your upper limit. And you say, hey, I computed this confidence interval. Look, your value is way outside the confidence interval. The guy says, buddy, that's a really impressive confidence interval, but it only contains the mean value of y, the mean price. And my car is above average. I have these wheels, this, that, stereo system. So what do you really want? You don't want an interval that contains the average price, right? You want an interval that actually contains the price. So we compute this thing called a prediction interval. So when I want an interval that contains the mean of y, it's called a confidence. But in regression, when I want an interval that contains the value of y, we call this a prediction interval. Okay? And we can do both in StatCrunch. So let me show you how it works. So confidence interval, it gives us the range of values that we think contain the average value of y. So if I pick out a specific value of x that I want to do a prediction for, okay, this would be the 95% confidence interval for the mean of y. This would be like the 95% confidence interval for the average Porsche price. When I want an interval that contains the true value of y, I compute this thing called a prediction interval. So I would say that I'm 95% confident that the price, not the average price, but the price for a Porsche is in this interval here. Notice the prediction interval is wider than the confidence interval. Does that make sense? Yes, because we know that averages have less variation than the variables, right? So averages have less variation than averages, so you can see that. Okay. So how do we do this? So here's how we do this in StatCrunch. Let's go back to the Porsche data set. And what I want to do is I want to figure out what is the 95% confidence interval for the average price of a Porsche having 50,000 miles on it. And what's the 95% prediction interval for the price of a Porsche having 50,000 miles? So go into StatCrunch, and all you have to do where it says prediction of y is type in 50. That's the value of x that you want to do the prediction for. Well, should I type in 50 or 50,000? 50, right? Because x is given in units of thousands, okay? And then we're just going to put the confidence level right here. And when you do, you should get some output. And let me see if I can finally get this to work to show you. I have a feeling it's not going to work for whatever reason. Okay. So I'm going to go around and make sure that you guys can at least do it. That function still not working. Yeah. I refreshed it 3 times. Which is okay because you have the instructions in the PowerPoint, so you can go back later. Did anyone get it to work? So, okay. So Nicholas has it. Okay. So when you can I listen to the oh, okay, thanks. Okay. So when you get it to work out, what you'll find is that at the bottom of the output, you'll see a new thing called predicted values. Okay. And so the 95% confidence interval for the mean. Can you read that off to me?
38, 379.
Okay, let me So when you look at the output, you'll see a new thing called what's it called? Prediction.
Predicted values.
Okay, predicted values. Okay. And so for the 95% confidence interval, what are the values?
38.379.
44.82, okay. And then you have a 95% prediction interval, right? And what are those values?
25 or 26.5 here. 56.
I'm sorry, what was the other one?
26.5 here. And 56.7.
So how do we interpret this? So here's how we interpret this. We say that we're 95% confident that the average price, and this is a key word, average price for a Porsche with 50,000 miles is between $38.8 thousand and $49.8 thousand. Okay? For the prediction interval, it's exactly the same wording except what? I take out the word average, right? So now I would say that I'm 95% confident that the value, not the average value, of a Porsche with 50K miles is between 26,500 and 56,700. Okay? So that's the difference between prediction and confidence interval when we're doing regression. And if it didn't get it to work out. All right. So I'm not going to go through this one problem. We probably won't have time. Because I want to talk a little bit about using and misusing regression, okay? So the first thing I want to talk about is the fact that when we do a regression model, we have to look at three things. First, we have to look at the question, is it valid? In other words, is it even okay for you to do regression? Which is another way of saying, have I satisfied the assumptions, okay? The other question we have to ask is it significant? You can have a valid model, all the residuals are normal, but there's no relationship. It's just a flat line, right? And that's when we do the hypothesis test on beta 1. But there's a third question you have to ask, which is just as important. Is it useful? If you have a significant model, but the fit is really bad, it's not particularly good. Notice, for example, in this prediction interval, is this really useful? I would say not that useful, okay? I mean, I'm saying basically the price of a course will be between, roughly 27,000 and 57,000. That's a huge range, right? So what would I do to improve that? How could I have got a better, a tighter prediction interval? How do I get more precise estimates? What's the principle? Larger sample size, exactly. So I should have taken a bigger sample, right? Now, it turns out that we can actually measure this. So notice we can answer the question is significant by looking at the output, right? We can also answer this question by looking at something called the coefficient of determination. And so what is that? Well, basically, it's the correlation coefficient squared. So we already saw that the correlation coefficient did double duty, right? It told us about the strength and the direction of the relationship. But it turns out that it also tells us how good the model fits the data. So when you square R, and people tend to write it traditionally capital R squared, this is called the coefficient of determination. And what this means, the way we interpret this, is this tells us what percentage of variation in the data the model can account for. Or conversely, if we look at 1 minus R squared, it tells us the variation in the data unaccounted for by the model. And so in the Porsche example, if you look at R, the correlation coefficient for the Porsche example was roughly about minus 0.89. And when you square that, the R squared is basically this squared, which is roughly around 0.81. So the way that we interpret that is we would say that the model accounts for 81% of the variation in the data. Do you think that's good or bad or on average? It's actually really good. Okay, so and this doesn't surprise us, right? Because what does R measure? R measures how strong the relationship is, right? So we knew that this was a strong relationship. This number, the absolute value is close to 1. So it's not surprising that this is a good R squared. Okay. Now, you're not responsible for the next 2 slides, but I want to show you this because if you're in human factors or Homeland Security, you'll see this later on in courses. People talk about this word account for variation. Here's how we think about this. The way we think about this is we think about the total variation first. In other words, this is the mean, and these are the deviations. So the total variation is actually like the variance. This is the total variation in the data. Then what we do is we think of the variation accounted for by the model. In other words, what I'm doing is I'm looking at the difference between the model and Y bar. So this is the variation between the predicted and the average value of Y. And we call the sum of all these squares the sum of squared errors. And finally, we have this last term here. So here we're looking at the residuals, right? This is the fitted line. These are the data values. And so this is called the sum of squared residuals. We take these residuals and we square them and we sum them up. There's a beautiful relationship that you get. It turns out that you can partition the variation. We can say the total variation can be written as the variation accounted for by the model plus the variation unaccounted for by the model. So there's this little formula that arises. Now, what does this have to do with the model and how well it fits? So these are our three terms: total variation, variation accounted for by the model, variation unaccounted for by the model. So let's think for a second. When the model's really good, should this be small or big? This is the variation unaccounted for by the model. When the model's good, it should be small, right? So now if I go ahead, I take this relationship and I divide by the sum of squared totals, this gives me the percentage of variation unaccounted for by the model. This is the percentage of the variation accounted for by the model, and that's actually what R squared is. Okay? And so I don't expect you to get into a deep understanding of that, but this is what it means when we talk about accounting for variation. Okay, so if you look at the StatCrunch output, and I'm not going to belabor this point, but if you look at this, you can convince yourself that the sum of squared model plus the sum of squared error, this is the variation accounted for by the model. The variation unexplained, this is the error in the model. The total, convince yourself to add up, and you can convince yourself that this divided by this gives us R squared. So you can do that, okay? So the last two things I want to talk about, one of them is correlation. So this is the sort of thing you hear in the news a lot, where someone will come on and they'll say, we did a scientific study and we showed there was a really strong, I'm saying in a kind of official version, very scientific, we have shown that there's a strong negative correlation between the incidence of breast cancer and the amount of bottled water people drink.
Yes.
This sort of stuff does come.
But did they prove it was real or was it fake?
Well, here's the thing. Even if it's real, let's go ahead and suppose it's real. There's really a strong negative correlation. What does that tell us? Does it tell us anything? Should we start telling women to drink bottled water? Women that are high risk for breast cancer, should we tell them to start drinking water now? Why not?
Should see if there's any ulterior reason why they're not drinking bottled water and if that has anything to do with it.
So there might be other things that are going on, like what? Yeah.
One of the biggest ones that I heard was they only studied people who had cancer, and they did you do A, and it 90% said, okay, there's a correlation there. Well, so they were only asking do you drive a car? Yes, 90% of people that or 99% of people that have cancer drive cars.
So these are all issues. So we have to worry about sampling. Let's go ahead and suppose that they sampled well. They really took a good random sample, so the sampling's okay. But so now should I tell women to start drinking bottled water? Does this say what is the implication? The implication is that drinking bottled water lowers the risk of breast cancer. Why is that conclusion not valid?
Is this a scientific experiment?
Yes and no. We'll talk about. There's kind of ways around that. That's not such a bad thing. But it is kind of getting close to the point.
It's like what he was talking about with the cars, the correlation is just not implied by the causation.
Why not?
Because it just doesn't.
So that's what people say, but why is that true?
Because taking one standalone variable doesn't take into account all the other variables.
Why? Right, other variables. So are there other things that could account for this?
Yeah.
Like what?
Every woman needs to drink water.
Okay, so genetics is one thing, but genetics, I don't know, maybe. Other reasons? Okay, so
they all drink water.
but bottled water, right? So what else could affect it though? Okay, what about socioeconomic status? Women that probably have more money drink bottled water, but what else do they probably do? They probably take better care of themselves. right? So there are other factors that might account for both of these, okay? So this is the problem. So like you say, famous phrase, correlation doesn't imply causation. So just because two variables are strongly correlated doesn't mean that they necessarily have a causal relationship. So kind of go to Gabe's comment. So there are situations where we don't do scientific studies and yet we can prove causation. So for example, smoking and lung cancer is a great example. I can't do a controlled experiment, right? I can't make you smoke and then study you, okay? But here's the thing, regression is a first step. Then you have to do more. And it turns out that you actually can show causal relationships, but you have to do a lot more work. Correlation alone is not sufficient. So these are two famous examples, okay? This is ice cream that's purchased in a town and the number of deaths by drowning. Notice a very strong positive correlation, right? But nobody in their right mind thinks that eating ice cream is causing people to drown. This is my favorite. This is number of ice cream sold versus murder rate. So as the murder rate goes up, ice cream goes up. So I guess people are excited when they eat more ice cream or scared or whatever. So what's going on with both of these? This by the way, is called spurious correlation. There's actually a website that just has a gazillion of these. What's actually going on is there's a third variable, a working variable, which here happens to be the weather, right? So as the weather gets better, ice cream sales go up, more people swim, more people drown, okay? Now this sounds funny, but you'll be surprised, especially when it comes to these medical trials, people do draw these causal inferences. And moreover, you see it a lot. Just, over the break, I read a really funny story, I think it was in the Sacramento Bee, where they said that they made this observation that the number of firemen at a scene was highly correlated with the property damage. And so they made it sound like the firemen were like, they were just sitting around drinking beer, trashing the place, right? This is a true story. But what's going on? Why is it that the number of firemen are highly correlated with the amount of property damage in a fire?
It's a bigger fire.
Exactly. I mean, but you see this sort of stuff a lot. This isn't that uncommon, okay? All right. So last thing I want to talk about is this issue called extrapolation. So what I want you to look at carefully is this right here. This is the range of X values we used to actually make the Porsche model, okay? So there was one Porsche that had 0.7 thousand miles and one Porsche that had 92,000. And the thing you want to take away from this is that we can use any value of X in this range to predict the average value of Y. Okay, that's perfectly legitimate, all right? But here's the problem. What if X is not in this range? And we just got through saying in the last class that, for example, we couldn't use this model to predict the average value for a Porsche when it had 0 miles, right? Because that's called a new car. That's not a used car. Notice how close this is, though. It's really tempting, right? So the moral of the story is that if you have a value like 100,000 miles that's outside this range, okay, even though you can find the value mathematically, it's not valid. And notice that if you keep on using this model far enough, what's going to happen? It's going to cross 0. So you're actually going to predict that at some mileage that there's a negative price, which means what? It means someone's going to pay you to take their Porsche. You know, what if that was true, right? So you have to be careful, okay? Now this sort of stuff happens in real life. So let me show you a real example. This was published in Nature, which is one of the most prestigious scientific journals. And what this person did was they analyzed the winning times for the 100-meter dash for men and women. And they extrapolated, that's what we call it, when we try to predict values that are outside the range used to construct the model. They extrapolated and said that by the year 2156, women are going to outrun men. They're going to be faster. Okay? You're nodding your head, yes. Who knows, right? Maybe. But here's the thing. Notice how far they projected out in the future. Now here's something fun. So somebody collected the times for the next 3 years. Okay, so these were the 3 years after the study was done. Look how it changes the line. Now that extrapolation doesn't hold. So just by going out 3 years totally changed that prediction. Okay, so this is the danger of extrapolation. Okay, but these sorts of things happen a lot. So extrapolations are really common. Let me see if I have it with me. I think I told you this before, but yeah. So this was like I said, this was in the magazine that statisticians, read, and the cover is this thing called Saving Bergen. Bergen's that town in Norway I was talking about. What's happening? Water levels are rising. They have to make predictions. So sometimes you don't have any choice, right? So how do you make good predictions? This is a hard question, okay? So here's the idea. Usually you don't try to project too far into the future, and you run models with a wide range of parameters. You run different models from different people with different ranges of parameters. Think back to Hurricane Katrina. Remember, everyone wanted to know where the path went. What did the news show you? Does anyone remember? When they were talking about the path, what did the news show you? They actually did a pretty good job of this. Did they show you just one path? What did they show? Right, so what was that spaghetti model?
All the calculated paths.
Right, they were models from different people using different parameters, almost like a confidence interval for the path, right? And the idea was that it was going to be somewhere in between there. That's the same thing we try to do here, okay? So predictions are a tricky business. If it was easy, we'd all be millionaires. We could all go on to Wall Street and just clean up. It isn't that easy, okay? Okay, so what you need to know, these things are all on the list, okay? So go through the list, check them out. And I think that's pretty much all. So download those two things, do the practice exam. We'll talk about that on Tuesday. If you need help, I'll be in my office all day tomorrow from 8 to 11 and 1 to 5, so feel free to stop by. All right, thanks. What's that?
Something along the lines of exponential growth.
Yeah, so exponential growth is a classic example of where if you look at bacteria, right, initially it starts exponentially, then what happens? It bottoms out, right? So that's actually called the logistic equation, the model of growth. Why is that happening? Well, because resources are getting really scarce, right? So now people can't grow as fast as they used to. But it turns out any sort of population, if you look at the US population, it falls that exactly. When the US started off, it was literally exponential. But then, people had to compete for resources, space, and now it's kind of plateaued out.
Yes.
Is that kind of what you meant?
Kind of. Yeah, isn't like U.S. population supposed to or not U.S. population, but world population is supposed to start at 11 billion?
Eventually, yeah. And I don't know the models they use for world, but the same thing's going to happen. Eventually, it's going to grow a lot, and eventually it's going to plateau off. And then what's going to happen?
Well, it's already started right now.
Plateauing out?
Yeah, it was like Russia, Japan, and China. The death rates are right now.
Yeah. And so the place where you're seeing the highest growth is mostly kind of like the African countries. Those are the ones that are showing the explosive growth. For reasons that I don't actually know. I'm not sure. So. You said one
Introduction of modern medicine.
Yeah.
I had because I have a flash right during your time.
Yeah, absolutely. I should be there. So yeah, please stop by.
All right. It'd probably be the more exposure to modern medicine.
Yeah, stuff like that. Aid. I mean, because you have Bill and Melinda Gates and these people going in and helping, and so it's kind of funny. It's like the law of unintended consequences sometimes. It's kind of interesting. Yes, sir.
So I emailed you probably a long time ago